This is a video lecture over section 2.1 plus a couple of extra topics. In this video, we'll be talking about stem and leaf graphs, or what we sometimes call stem plots. We'll be talking about dot plots, and we're just going to have a quick word about the graphs for categorical data that you're already familiar with. We're not going to spend a whole lot of time on those because those are prerequisite material. Our main focus will be on stem and leaf graphs and dot plots. Let's start with the definition of a stem and leaf graph. A stem and leaf graph, or stem plot, is a graph for quantitative data that uses the digits in each piece of data to organize the data into classes. That is the definition of a stem and leaf graph. It's not very enlightening. It doesn't tell you what a stem and leaf graph looks like. It doesn't tell you how to create a stem and leaf graph. So it's lacking a little bit, and we'll get into those things. But I want to point a couple of things out about this definition before we go on to talk about how you create one. First, I want you to notice that this is a graph for quantitative data. So you're going to be working with numbers in this case, and that's given away by the fact that it says we're going to be using the digits in each piece of data. So the data has to be numerical, and in fact, step further, it has to be quantitative. Secondly, we're going to be organizing the data into classes, much like we do in a grouped frequency table. But the advantage that a stem and leaf graph will have is that we'll know what every piece of data is. When you create a grouped frequency table, you don't usually know what the individual pieces of data were, you just know how many fall into a particular class. With a stem and leaf graph, not only do you have them organized into classes, but you've also represented each piece of data with its actual digits, and so you know what the data is. That's not to say that stem and leaf graphs don't have their drawbacks, they do, and we'll bring those up. But one advantage that a stem and leaf graph has over a grouped frequency table is that we're actually going to know what the data is in this case. So how do you create a stem and leaf graph? It's kind of a three-step process. First, we're going to imagine mentally dividing each piece of data into two parts. So I'm going to do this for a simple example. Suppose I had a number like 58, two-digit number. I'm going to imagine dividing that into two parts between the 5 and the 8. So I get a leading digit of 5 and a trailing digit of 8. That leading digit of 5 we would call the stem, and the trailing digit, the 8, is what we call the leaf. So with this division, the stem would be 5 and the leaf would be 8. If you're thinking ahead a little bit, you might say, well, what would you do if you had a 3-digit number or a 4-digit number where you have options? How would you know how to divide those up? We'll get into that, and in fact, step 2 will give us a little bit of insight into how we might make that choice. Step 2 says, organize the stems in a column, beginning with the smallest and incrementing by 1 until you reach the largest. Do not skip over stems that do not occur in the data set. So we're going to identify the very smallest stem, list that one first, and then counting by 1, we're going to build all the way up to the largest stem. If you've made a choice for dividing the numbers up in such a way that you wind up with 90 stems, that's not going to be a very good graph. It's going to be very difficult to read. We're going to want a reasonable number of stems, somewhere in that 5 to 20 range that we mentioned for frequency tables. We want a similar rule of thumb here. I'll show you with an example when we have an actual choice. When you've organized the stems into a column, you create a bunch of rows, and so we just place each leaf in the appropriate stem row. Some authors will tell you that you need to then organize the numbers from smallest to largest in each row. We're not going to bother with that. I think you still get a really good graph, even if you don't take the time to organize the leaves from smallest to largest. Even with these steps, you still probably don't really know what a graph looks like or how to create it. So we're going to go through two examples. An easier example where every piece of data is 2 digits, and then a slightly more complicated example where we have to make a choice of how to divide it up before creating the graph. For our first example, I went onto the Madden website and found the overall ratings for some skill players on offense on a particular team. I chose a team in the NFC East with a star on their helmet, and I selected out all of their quarterbacks, running backs, receivers, and I found all of their skill ratings. For those of you that are familiar with Madden, I started playing that in 1993 and gave up on it when your controllers had more than 3 buttons. Video games are way too complicated for me now. And for those of you that aren't familiar with Madden, these player ratings are a big deal to some of the players. They actually care about what score they're given, so to speak, in the video game. It tells you how good their character is inside the game. Now, every rating that we have here has 2 digits in it. So trying to decide how to divide each piece of data into a stem and a leaf doesn't take much effort. With a number like 93, we're going to split that right down the middle and create a stem of 9 and a leaf of 3. And with 92, we're going to create a stem of 9 and a leaf of 2. And we're going to imagine doing this to each piece of data in the set all the way down to 57, which will have a stem of 5 and a leaf of 7. So you want to visualize what it would look like to divide each piece of data up. So we're going to do this on another slide here. I've taken the same data set, kind of smashed it up at the top so we'll have a little more room. So again, imagining breaking each piece of data into 2 pieces, the very smallest leading digit will be 5, so I'm going to start with the 5. And the very largest leading digit will be 9. So I'm going to increment by 1. I'm not even looking at the data set to see if there are any pieces of data that have stems in between. I'm going to increment by 1 until I reach that largest stem of 9. So 5, 6, 7, 8, 9. I'm going to divide those stems off with a little line. That should be a line. It's kind of wavy, I know. And you can see I've created a bunch of rows. I've created a row for numbers that begin with 5 and a row for numbers that begin with 6 and so on. And this data has already been organized from largest to smallest. So if I just march through it from last piece to first piece, my data will actually be in numerical order. So 57 has a stem of 5, so I'm looking at the first row, and it has a leaf of 7. So I'm going to place a 7 here. We understand that that means 57. Sometimes you'll see these graphs drawn with a key to kind of explain what the very first piece of data means. So kind of off in the margin or above or below, you'll see something that says that this means 57. No need to explain the rest of them. That key should give you an idea of what the rest of the data values mean. Again, working from back to front, we have 61. I'm going to place the 1 directly under the 7, so it makes it easy to compare different stem rows. 62. No comma, no semicolon, just a little bit of space. And in fact, if you look at a printed one, sometimes there's almost no space. I don't think that's a very good idea. I think it would be better to have a little bit of space in there. But if you have a lot of numbers in your data set, you do need to kind of smash them together. There's another 62. I don't need to do anything special with that. I just write another 2. I should be trying to keep the spacing between these equal. This is exactly why we use technology nowadays to make graphs, so that you don't have to measure things with a ruler to make it look nice. I don't want you to worry about that too much. I just want to show you what these look like and how you read them. 65, 67, 67, 69, 69. I go into the 70s now. There's a 70. And then another 70. Notice that I'm trying to line these up. 72, 73, 75, 75. In the 80s, there's an 81 and an 84. And in the 90s, there's a 92 and a 93. Aside from my sloppy handwriting, that's basically what a stem plot should look like. You can see that it's organized the data into classes. The first row is the class from 50 to 59, and the second row is the class from 60 to 69, and so on. So we've organized the data into classes. But beyond that, you can also tell what data actually lives in the set. Like you can see that the very lowest scored isn't just in the 50s, but in particular it's 57. And the very highest rating isn't just in the 90s, but in particular it's 93. If we had just turned this into a grouped frequency table with classes that were equivalent from 50 to 59 and so on, it would tell us that there was one number from 50 to 59, but it wouldn't tell us what it was. We'd have no idea without looking at the raw data. So this gives you similar information to what a grouped frequency table would give you, but with telling you the actual pieces of data. Kind of nice. And again, it might sound like I'm trying to sell you on these being better than grouped frequency tables. I'll let you know one of the drawbacks to these things after I've shown you a second example. For my second example, I looked up how many pages were in some popular books. They were on bestseller lists. And I listed some of those page counts below. I have 21 different page counts listed here. They all fall in the hundreds, and I chose this example not because I thought you'd be especially interested in knowing how many pages are in popular books, but because I knew this data would have 3 digits for the most part. And it's going to give us the opportunity to talk about how we would divide this data up. So I'm going to start with that very first piece of data, this 246 page book. I actually have 2 options for how I could divide that up. I could take the 246 and divide it so that it has a stem of 2 and a leaf of 46. Or I could divide it so that it has a stem of 24 and a leaf of 6. How do we determine which option is better? By looking at the rest of the data as well. And if you scan it really quickly, you'll notice that this goes all the way up to 898. Let's talk about how you would divide that piece of data. In the 1-digit stem, we'd get a stem of 8 and a leaf of 98. And in the 2-digit stem, I'd get a stem of 89 and a leaf of 8. Keep in mind our rules. We're not allowed to skip over stems that do not occur in the data set. That'll give us 7 stems, and there might be other stems because there could be a stem smaller than 2, and in fact there is. But somewhere in that range, 7 or 8 stems. If you look at the second example, with what we have right now, the difference between these is 65, which actually means there would be 66 total stems counting from 24 to 89. And a lot of those would be blank. This option would not be good for this particular data set. I'm not saying that in all examples with 3 digits, you should split the data with a 1-digit stem and a 2-digit leaf. It depends on the data that you have. But this particular set of data seems to work better by using a 1-digit stem and a 2-digit leaf. If we chose a 2-digit stem and a 1-digit leaf, we just wind up with way too many rows, and again, lots of them would be blank. You want to choose to divide the data in such a way that you wind up with a reasonable number of rows. And what do we consider reasonable? The same thing we considered reasonable for a frequency table, somewhere in the range of 5 to 20. There are certainly examples where pulling off 5 to 20 rows isn't possible. In a case like that, maybe you just shouldn't use a stem plot. You should use some other graph. Getting back to our example here, we're going to imagine mentally dividing each piece of data into 2 parts with a 1-digit stem and a 2-digit leaf. The smallest possible stem will be 1. It occurs a couple of times here. The largest possible stem will be, 8 we said, right? So I'm going to list all of the stems from 1 to 8. I'm going to divide them off from the rest. And now I'm going to go through the data set and just write each leaf in the appropriate stem row. And here the data is not organized from smallest to largest to begin with, and I'm not going to bother to do that. I'm just going to write each leaf in as I see it and go from there. I'm going to have you guys watch me write a few down, but I'm not going to make you watch me fill in the whole thing. I'll edit out filling in the entire table, but let me do a couple of them with you. The first piece of data is 246. It has a stem of 2 and a leaf of 46. So in the row created by the 2, I'm going to write a 46. And then the very next piece of data also has a stem of 2 with a leaf of 72, so I'm going to leave a little bit of space and write 72. The next book had 572 pages, so kind of in line with the 46. I'm going to write a 72 in the 5 row. And then 192. 208, you really do want to write 08 so that you can imagine concatenating those digits together to create a single 3-digit number. 452, 412, and I think you get the point, so I'm going to fill this in quickly, edit it out so that you don't have to watch me do it, and I'll show you the final product. We'll talk about it. Here's the finished product. It again gives us a visual representation of classes of this variable. Here the classes range in hundreds instead of in tens like in the previous example. So the first row ranges from 100 to 199 pages, the second row ranges from 200 to 299 pages, and so on. In case we were worried somebody didn't understand what this meant, we might give a little key that, for example, 1 line 92 means 192. And what we see here is the pattern of variability for this data set. I can see that the data tends to be lumped in the 200 to 400 range. There weren't a whole lot of bestsellers in my data set that had fewer than 200 pages. There certainly wasn't very many that had more than 400 pages. We see this big gap, and then we've got this kind of anomaly that sits in the 800s. And that gap allows us to easily identify that this number is kind of strange. We call a number like this an outlier because it sits so far away from the rest of the data set. But being all on its lonesome like that is much more striking because we left these stems in there even though they didn't occur. That's exactly why we want them in there. It gives us an idea of this pattern of variability. And even though I didn't bother to organize the stems from smallest to largest, you can still quickly identify what the smallest piece of data and largest piece of data is. The smallest piece of data would come from pairing the smallest stem with the smallest leaf in that row. So 192 or 128. Well, 128 is the smaller of the two leaves in that row. And so the smallest piece of data is 128. The largest piece of data is very easy to identify in this example because there's only one leaf in the largest row. But if there were multiple leaves in the largest row, we would have just found the biggest one of all and paired it with that stem. So stem and leaf plots give us lots of useful information. We can quickly determine things like the smallest piece of data, the largest piece of data. We get an idea of the pattern of variability. What are the drawbacks? Stem plots are a poor choice when there is a lot of data or when there is very little variability in your set. Obviously, if you have thousands of pieces of data, you're not going to be able to make a stem plot. It's just going to be too big horizontally. You're going to have too many leaves to fill in each row. So you can't use a stem plot when there's a lot of data. A grouped frequency table, or the graph that goes along with it, would be a much better choice in a case like that. The other time you can't really use a stem plot is when the numbers are really bunched close together. Suppose I had a set of 2-digit numbers, but they were all in the 20s. Right? So there's not a whole lot of variability in the set because they all range in the 20s. Creating a stem plot for an example like that would be silly because there'd only be one stem, 2, and then an extremely long row of leaves after that. It would look essentially like the original data set, but with all of the leading digits lopped off of the front. You couldn't create a stem plot in an example like that. What could you use there? You could go with an ungrouped frequency table. That would be a good option. Or another option would be to use the next graph we're going to talk about, which is the dot plot. A dot plot is a graph for quantitative data that represents each piece of data with a dot placed above a horizontal axis, which measures the value of the variable. Here, this definition gives us a little more of an idea of what the graph looks like. It's going to be a series of dots placed above a horizontal axis, but it still doesn't tell you exactly what's going on, so we're going to go through the steps for creating one. Before I do that, let me again point out some things about this definition. This is for quantitative data as well. And secondly, we're going to be representing each piece of data in the set. Just like with stem plots, that's going to be advantageous in one sense, and it's going to be a drawback in another. We'll get to that in a moment. Let's go through the steps for drawing a dot plot, and then we'll do a single example. I don't think you need to see multiple examples of this. 2 steps for drawing a dot plot. First, draw a horizontal axis to measure the value of the variable. So you're going to draw like a number line where you can mark off, measure the value of the variable. And then for each piece of data, you're just going to place a dot above its value on that number line, on the axis. If you get a repeated value, you just stack the dots vertically. So here's our set of data. I found the number of semesters it took some students to complete a bachelor's degree. The old convention was that a bachelor's degree would take you 4 years, which is 8 semesters. That's no longer the case, and you can see that reflected in this data set. Before we draw the dot plot, I'd like to point out that this data would not work well for a stem plot because there's not a whole lot of variability. I think we have enough room to do it here on this screen. So let me start by drawing an axis. I'm going to scan the data quickly, and I see that the smallest piece of data is 7. So trying to make it pretty on the left by putting a 6 over there or something, I'm not going to bother with. I'm going to count by ones, 8, 9, 10, 11. This is an axis, so I should be trying to space these equally. 12, 13, 14, and 14 is the biggest piece of data in the set, so I can stop there. I could put a 15 over there to make it look nice. If I really wanted to make it look nice, I'd probably redraw it, but I'm not going to make you watch me do that. And now, to draw the dot plot, we're just going to go through each piece of data and place a dot above the locations that we've just earmarked for each value. So for example, with 11, I find 11, I'm just going to put a dot right above 11. Then 8 at the same height, and then 10. Then I get my second 8, so I just stack the dots. And I've got 2 dots above 8. Then I get my second 10, and again, I'm going to try to keep these at the same height. 2, and then 3 8s. And then I get my first 9. And then 10 again. And then 10 again. And then 14. I'm guessing you see how this is working, so I'm just going to jump straight to the finished product. Now you can see my graph, and I didn't put my axis down low enough, so let me do one more quick edit where I move this down a little bit so you can see it better. There, that's in a better spot now so that my dots aren't running into my data set. So you can see what we've essentially created here is the graph form of an ungrouped frequency table. You can see how many pieces of data fell into each of those ungrouped classes. I can see there's 1 7 and there were 5 8s. You can quickly tell without even counting that there were more students who took 10 semesters than anything else. You can see there was nobody in the data set who needed 13 semesters. There are other things you might notice, like that the stacks on the odd numbers seem to be smaller than the stacks on the even numbers. That might be because a lot of students take 2 semesters a year and don't take classes in the summer, and they finish up in the spring, which is very common for students. All kinds of things that you can tell about this. You can see the pattern of variability does not really appear to be a perfect bell curve, but there is kind of a peak in the center. So we like this graph because you can see each piece of data. It's a nice visual representation of the data set. Drawbacks? Well, you can't create a dot plot when the data set is large here either. If you have thousands of dots to draw, it's going to be impossible to read the graph. You also don't want to use a dot plot when there's little or no repetition. If the data values aren't repeated, if each value occurs exactly once, then what you'd wind up with is an axis with a row of dots sitting above it. And that's no better than the original data set. You just have a line of points sitting right above the axis instead of getting a nice graph like we did in our example. So you shouldn't use a dot plot when the data set is large. You shouldn't use a dot plot when there's little repetition. There are 2 other graphs that the authors mention, and I want to bring them up, but we're not going to spend any time on them because I know you've learned about them in prerequisite courses. Bar graphs and pie charts are very commonly employed graphs. The only thing I want you to know about them for our class is that they are reserved for categorical data. Whereas dot plots and stem plots are for quantitative data, bar graphs and pie charts are usually used for categorical data. So I'm not going to go into any specifics on how to create a bar graph or a pie chart, or even how to read a bar graph and a pie chart. The only thing I want you to know is that bar graphs and pie charts are for categorical data, and the other graphs we'll talk about in this class are for quantitative data. If you personally have any questions about reading bar graphs and pie charts because you aren't familiar with it, feel free to ask me. You can also ask me questions about the other graphs in this section if you're not familiar with them. Just shoot me an email or catch me in an office hour.